Welcome everybody. I welcome all of you to this course on digital communications. The subject number is EC34007 and it is a 310 type course, which, as you know, means that we'll have 3 lecture hours a week and 1 lecture hour will be devoted solely for the purpose of tutorial. We'll discuss about the tutorial and the way we propose to conduct it later. Today in this introduction we will discuss about the syllabus as outlined for this course, and then I'll make a few comments and I'll suggest some way which I would prefer to follow, provided you permit that. First, I'll reproduce the syllabus, and for the sake of better understanding, I have separated these topics so that I can take them up briefly for an introductory discussion. The first topic, as it should be, is on introduction to digital signals. And systems, spectra, and bandwidth. Let me write BW in short. Now, as you have learnt enough of signals, both analog as well as digital signals, in an earlier course on theory of signals and systems, which is a compulsory course nowadays, I suggest that I skip this and elaborate discussion on digital signals and systems. We will have a brief reference to the signals and their classification sometime later. Coming to digital systems, yes, that's the major topic for our discussion broadly. We'll be talking about various digital systems, wherein we'll talk about some coders, decoders, modulators, demodulators, receivers, and things like that. So, which can broadly be classified as some digital systems. Then, as you have already undergone a course on analog communications, so I assume that you have got a basic understanding about spectra as well as bandwidth of a band limited signal. We'll discuss, with the basic assumptions, we'll consider and cover a bit more on spectra and bandwidth of digital signals. The next major topic, as I feel, is on A to D conversion and quantization. This will lead us to the concepts of various speech coding schemes such as Dpcm. I shall get back to these acronyms later. PCM, log PCM, Dpcm, ADPCM, DM, ADM, and LPC, primarily for speech signals. The next topic as per the syllabus is on what is known as time division multiplexing, or TDM in short. This is an alternative to the more classical form of multiplexing, which you have already learned as frequency division multiplexing. After elaborating the basic concepts, we shall briefly take up the issue of digital hierarchy. And some familiarization with some popular standards. The next major topic is on baseband transmission. Data regeneration and clock recovery. The subsequent topics are like this. We should discuss about what is called as inter-symbol interference. And some of its solution mechanisms, mainly equalization. The next major topic is on digital modulation and demodulation. We will take up several forms of digital modulation, both binary and MRE, ASK, FSK and the like. The syllabus suggests we cover GMSK, PSK, Dpsk and their spectra, circuits, I am writing CKTS, and systems. Carrier recovery is a related issue. Performance of various digital modulation schemes is obviously an important issue for better understanding, for designing systems which works nicely, and also for assessing the limitations of various modulation schemes. The syllabus ends with the topic on elements of information theory and coding. Yeah. So this is the syllabus outline. I shall get back to this syllabus, explain a little bit, and then I shall suggest the approach that I have in mind. As I said, we must be familiar with various forms of digital signals and systems and their spectra, or equivalently bandwidth occupancy. There I will assume that we have sufficient understanding about analog signals and their bandwidth. We will highlight the special features of digital signals from time to time. Analog to digital conversion is a very basic process which usually is coupled to the input stage of a digital communication system. Before we think of processing a signal using a digital system or even calling a signal a digital signal, we must carry out this operation of conversion an analog signal into an appropriate form in the digital domain. And you must have observed already that many of the signals which we derive from the physical world around us, they are inherently analog in nature. So if we propose to transmit these signals digitally, it is obvious that we have to think of converting this analog signal digitally, and while doing so we have to ensure that this process of conversion does not introduce inaccuracies, at least not beyond a limit, so that the ultimate quality of the reproduced signal somewhere in the receiver is always satisfactory. We will discuss about some basic conversion schemes. After converting an analog signal comes the issue of representing the signal, or the signal sample to be precise, and for that we use an approximate method called quantization, and after quantization we represent the quantized versions in various ways. Some of the ways are noted here, like PCM, which is a popular technique used very extensively in many practical systems, stands for pulse code modulation. A variation of pulse code modulation is known as log PCM or logarithmic pulse code modulation. There is a need, as we will appreciate later, that we go for some operation called expansion, compression and expansion in a non-linear manner, and there a logarithmic compression and expansion makes practical sense. So log PCM is one such variety of PCM. We should discuss about this. Another very interesting variant of pulse code modulation is known as differential pulse code modulation, or Dpcm. We will see that the purpose of differential pulse code modulation is to reduce the average number of bits that otherwise would have to be transmitted following a more classical PCM technique. We will appreciate that transmission of digital signal through some wireless medium needs some transmission bandwidth, and if the bit rate, average bit rate of transmission is higher, we need higher bandwidth, while every other features of the system remains constant. So it makes sense that we try to reduce the bit rate of the signal which has been digitized. Dpcm is one elegant way of carrying out and serving that purpose. An advanced version of Dpcm is known as ADPCM or adaptive differential PCM. we will have a unit in a PCM coder and decoder which we'll call as a predictor. This predictor, if it can adapt itself depending on the temporary nature of the inputs signal samples, then the process of differential pulse code modulation is even more effective or efficient, because it reduces the transmission bit rate further, probably without compromising the signal quality. So ADPCM is a more advanced and more effective version of DPCM, but there will be some limitations in the form of complexity of the coder and decoder. We will have some discussion on ADPCM. Next comes a very simple method of coding and quantization, which is known as delta modulation. The concept is very interesting, simple, though it does not help us much in saving the transmission bit rate. Similar to somewhat DPCM and ADPCM, we have an adaptive version of delta modulation. So ADM stands for adaptive delta modulation. We should discuss a little bit about ADM. Incidentally, DM is also known as LDM or linear delta modulator. Then LPC stands for linear predictive coding. This is an important speech compression technique which results in great saving in average bit transmission rate, and thereby saving of the bandwidth that will be necessary. However, the complexity may be a bottleneck for rather simple applications. Notwithstanding, LPC at the moment is a very popular scheme for in many practical systems where complexity is not the only issue. After this discussion on signal conversion, quantization and various forms of coding, as I mentioned just now, we will take up the issue of time division multiplexing, wherein we will talk about how we can combine individual signals represented digitally and coded by any of the above schemes from various users, how we will combine them and will make them ready for further processes of modulation, transmission, reception, demodulation, etc., and ultimately the reverse process of demultiplexing at a receiver end, so that the individual signals can be sent to the original destinations without any interference. So we will talk about the concept of time division multiplexing, and then we take up what is called as the TDM hierarchy or digital multiplexing hierarchy. We will talk about at least two standards there, one followed by CCITT and the other followed by ITU or International Telecommunication Union. The next topic of baseband transmission is a very central one for the understanding of signal shaping, digital modulation, digital reception, there is demodulation and other related techniques. So baseband transmission will be discussed in rather detail, wherein we will also take up the issue of signal design. I will talk about signal a bit more sometime later. Inter-symbol interference is a limitation which is found in many occasions when we try to send pulses from one place to the other one, because we know when we try to reduce the bandwidth of a signal, the signal duration in time domain increases, which means that if we have an occasion to transmit at a very high bit rate, then if the transmission bandwidth is limited and the signal pulses are not designed properly, there is a possibility that the energy of a single pulse spills over its duration and interferes with adjacent pulse symbols. This issue is rather intricate and many times it limits the performance of an otherwise well designed digital transmission system. So we should discuss briefly about inter-symbol interference. a whole gamut of solution is already available to counter or at least to contain this issue of intersymbol interference. They are broadly known as equalizers. If time permits, we will discuss a little bit about a few very classical and fundamental equalization schemes, and will bring out their limitations as well. Digital modulation and demodulation, as I said, is a very important issue, because that is how we translate the basic signal represented digitally from one frequency band, which I can now call as the baseband or the basic bandwidth of the signal, to a rather high frequency band, which may be called as intermediate frequency IF, or even an actual transmission bandwidth, which is called as RF or radio frequency bandwidth. Digital modulation and demodulation process helps us in translating this baseband signal appropriately around the carrier frequency, such that the signal is well behaved and the message or information contained in that modulated signal is preserved while the signal around a transmission frequency is transmitted and it gets affected by noise and other disturbances. So, with good signal design and good choice of digital modulation and demodulation schemes, we propose to transmit a digital signal from one place to a distant one and receive them appropriately, so that the received signal quality is satisfactory to the end user. We will have occasions to discuss about several modulation schemes like FSK, frequency shift keying, ASK, amplitude shift keying, GMSK, Gaussian minimum phase shift keying, PSK, phase shift keying, Dpsk, a variant of PSK known as differential phase shift keying. We will discuss about their concepts, we will discuss about the basic technique, how we can modulate such signals. We will also discuss about how we can demodulate such modulated signal to get back the original data. We will talk about the spectra, and we will have good idea about the circuitry, but never at the most basic level of components of resistors, capacitors, etc., but at a sufficient detail, so that with your background of electronic circuits, both analog and digital, you should be able to design these circuits rather easily. Carrier recovery is an issue which is necessary for many of the demodulation schemes, especially the demodulation schemes which are known as coherent demodulation schemes. We will have occasions to discuss about these carrier recoveries later. Performance of digital modulation schemes, as I said, is a very important issue, but in this basic course or first course on digital communications, we will rather be limited to the performance and thereby the limitations of the various modulation schemes only in presence of what is known as additive white Gaussian noise, or AWGN, which means that we shall not take up the performance of the various digital modulation schemes in presence of any interference or other problems which may crop up in the channel during transmission of the signals. The last topic as per the syllabus is on elements of information theory and coding. Incidentally, information theory forms a basis of the whole gamut of digital transmission schemes. This is a classic theory developed by, whose development primarily started with pioneering activities of several scientists in 1940s, namely Claude Shannon, Hamming, Elias and others, and this resulted in the development of strong theory of what nowadays is known as information theory. Information is something which needs definition. We will have a definition of information subsequently, and we will probably have a somewhat different perspective of the basic problem of digital transmission. Information theory on the whole helps us in identifying the potentials and limitations of a digital transmission system, and more precisely of that of the channel in between the transmitter and the receiver. Coding in full, which may be called as channel coding, is another important area which have developed significantly over the last 5 decades or so, which in its own merit is a separate subject altogether. But in this basic course, our intention is to introduce some basic concepts related to information theory and channel coding, so that you go with a basic idea about what these concepts are and how they are useful to the study of digital transmission schemes. Coming to my proposal of how I suggest to cover this course, the first issue is that the syllabus is extensive, whether you like it or not, and we will try to cover as much as possible within the given time, and I shall try to make a balance amongst the topics which have been suggested in the syllabus. And in fact, from that point of view, my feeling is that maybe it's a good idea that we start with the last topic of information theory and channel coding, discuss about what is information, why information is important fundamentally in a digital communication system, and in the process we will also see what precisely is digital in a digital communication system. Is it that the signal is always digital in a digital communication system? Well, you may wonder, but we will see, and ultimately I hope you will agree that it is not necessary, and it is not usually so that the signal is always digital in a digital communication systems. In fact, in significant portion of the digital communication systems, for good reason, we will have the signal in a very known analog form, but still we say the whole system is digital. Why? Is a very common question, and as an answer to that, I shall try to introduce the concept of information, thereby creating two different concepts really. One is that of dealing or describing a digital communication systems through information, wherein I would like to establish that a digital communication or transmission system essentially is an information processing system whose end purpose is to take the information from a transmitting user, ensure that the information is delivered with as minimum distortion or error as possible to the designated destination. So the whole description may be at a somewhat abstract level, may be in the form of information rather than talking about signals here and there. In fact, that is one very important aspect which is obtained from the study of information theory. So we will have a brief feeling of that. Coding or channel coding is a very important aspect, at least from information theoretic approach of digital communication systems, wherein the issue of error in a channel comes up very soon, and then one has to think about how to protect the information in the event of such errors. And hence, several methods have been suggested naturally to contain the effect of these errors. Errors we will see are unavoidable because fundamentally of sources like noise, as I said, additive white Gaussian noise some time back, or otherwise from other interference, or maybe because of fading, etc., as you may be hearing nowadays. So we will also discuss about the basic concept of channel coding. I guess this initial discussion on information theory and coding will help us to bring in at least a different concept of, maybe somewhat abstract, of information processing in a digital communication systems, and then it will perhaps appreciate the need for a very good and precise representation of information in terms of signals. Signals are time varying quantities which are closer to us so far. So I propose to take up information theory and coding after we discuss some introductory aspects of digital communication systems. In the tutorial class, we will take up various related problems topic wise, and you have to submit the assignments in time. they will get corrected and you will get the feedback. So, in this theory or lecture hours, we may not discuss in detail about several problems. We will also assume that, as I said, you have got some understanding about digital signals and both analog and digital signals, and some idea about digital systems because you have gone through a course on digital electronics. I shall also assume that you are also equipped with some mathematical tools such as Fourier transformation, Fourier series expansion and the like. Traditionally, it is traditionally we also discuss about a very important topic, what is known as probability and stochastic processes. In fact, that should be, without an understanding about probability or and stochastic processes, discussion on digital communications may not be relevant. But again, I assume that you have got basic understanding about probability theory and random processes through other courses. So, in this course, we will not discuss much about various properties and features of stochastic processes or random processes or even probability theory, and we will assume certain basic knowledge on that for topic discussions in this course. Let me tell you about some additional resource materials. I suggest that each of you purchase at least one book of your choice, because this is going to be a good companion of yours if you have some interest in digital communications. And well, the subject is rich, and hence there is no dearth of good books in this area of digital communications. There are many classic books. I have listed only a few of them which are presently available readily, and even I guess, yeah, all of them are rather low cost editions. So, my suggestion of purchasing one book for each of you makes sense that way. Well, I have listed only a few here. I mean, I could name a few more, but the list is already good enough for you. Like, I guess you have already you are familiar with this book by A.B. Carlson on communication systems. This book covers aspects of both analog as well as digital communications. The emphasis is on both. This is a very nicely written book with a good balance between qualitative discussion and mathematical rigor. That is one aspect of this course. Let me tell you, without frightening you, is that the subject, good understanding of this subject needs some love for mathematics and mathematical tools. If you are fond of mathematics, perhaps you are the person who will appreciate the this course on digital communications more. And there is no end to this really. The subject, one approach, one way of looking at it is that it is highly mathematical, and if you are comfortable with mathematics, then you are the person who is likely to have more insight to what happens, to what more can be designed and developed in this area of digital communications. Well, so that way Carlson's book is a good balance, I should say, on both a qualitative aspect, which is fundamental at the introductory level, which is important at this introductory level, as well as the mathematical description of the same. Wherever it is necessary, it is there in a precise manner. So, this is a good book, and it is there in my list. The next book by Taub and Schilling is a very widely referred classical book. It is available for a long time now. The title is on Principles of Communication Systems. Again, the book has important chapters both on analog communication, issues of analog communications as well as digital communications. So, if any of you have referred that, I guess you have loved the book, because this book is a very lucid one. At least it is lucid to me. Okay? And the special reason I have listed this book is that this book has got all the chapters are worth reading. It has got at least one full chapter on baseband transmission and the effect of noise, basic visualization and mathematical interpretation of noise a additive white Gaussian noise, which is fundamental to the understanding of performance and limitations of various digital modulation schemes as well. So this is a very, very good book, a lucid one. Balance between mathematics and qualitative analysis, I say, is a very good one. Okay. Digital Communications by Simon Hakin is a relatively recent book, I should say, on digital communications only. The author has got several books, but this book on especially digital communications is again a classic one, I should say. It's not a very thick book, but is an excellent balance between the underlying concepts and the mathematical rigor. The mathematical treatment is very precise, very interesting, and it gives very interesting aspects to many important concepts therein. Digital Communications by Proakis, J.G. Proakis, is a thick book, I must say. It's full of mathematics, implying thereby that the balance is more towards mathematics. Qualitative discussions are also there. Yes, you get intuitive ideas, but the focus is evidently on mathematics, on precise development of ideas through mathematics. So those of you, I guess many of you already have inclination for further knowledge on digital communications, they should consult this book, okay, because at the advanced level this book on digital communications by Proakis should serve as a very, very good reference. I guess, yeah, I have a few more books to list here. As I said, there is no dearth of good books, really, very exhaustive books like this one on digital communication techniques, jointly authored by Simon, Hinedy and Lindsay. It's again a compilation of voluminous work, some of their own, and this is where, I mean, in addition to other places also, you will get a more information theoretic approach to digital communications. If you remember our last topic as per the syllabus, this book has got good emphasis on issues like carrier recovery, carrier synchronization, symbol timing recovery and topics like that, while discussing about all other important issues. Digital and Analog Communication Systems by K.S. Shanmugam is again a very precise, very handy book with a good balance between intuitive ideas and their mathematical treatment. Is a very nice lucid book, I should say. Digital Communications by Bernard Clark is again a very voluminous book, but it is a very lucid one, I should say. The emphasis is more on qualitative discussion, coupling it with mathematical treatment wherever necessary. So for bottom line description, Bernard Clark's book is a good reference. All these are my opinion, just to help you out, but I suggest you go through all these books. Most of the books are available in fact all the books are available in our library and they are also available in the market. So go through them and try to have at least one book. Now, before we end today, let me take up a very simple issue of, very simple question of what is digital communications? What is it really? Is it that communication has to be done digitally? Like, let me ask really, what is digital communication? As I said, that I understand that you have already gone through a course on analog communication. So I'll be happy if you can answer this question at least by saying that why it is not analog communication, or how this is going to be different from analog communication. What is digital about this? Digital here? Is it that? Is it that? Well, I have to complete this diagram perhaps. Let me say that you have a source somewhere or signal source, should I call that a signal source from which we get a signal. Like in analog communication system, we get an analog signal from a source. The source may be a human being, okay, and we get an electrical signal here which is analog in nature. And the purpose of any communication system or transmission system is that this signal has to be transferred to another place. Specifically for a communication system, when you differentiate this communication system from a one-way broadcast kind of system, we can say that the purpose of a communication system is to establish a connectivity so that signal from source, let me say source number 1, can be taken to another user, okay, and then if user 2 also behaves as a source, which we normally assume, then calling him as source number 2, then the signal from source number 2 also will have to be linked to source number 1, wherein source number 1 will behave as a destination of this signal, which means that a communication system essentially has to be a two-way system. That means we have to, there has to be links between a pair of users, okay, such that they can communicate amongst each other. Well, so with this in mind, for a communication system, I am talking about both analog and digital at the moment, can I say that on the whole there has to be a device which I can call as a transmitter or TX in short, so that signal from source 1 can be taken and some signal processing can be carried out and something can be generated from this transmitter, which will go through what I shall broadly call as a channel, and at the other end of the channel we will find another device which let me call as a receiver Rx, which will try to get back the original signal and will ultimately deliver to the user or end user, receiving user. This is a very fundamental description of one way of this two-way system, communication system. So it's natural that for a communication system there has to be another associated block with this receiver of second user, which I should call as TX, for transmitting signal from source number 2 towards source number 1. And now think a little bit, this signal may or may not pass through the same channel. That means the channel for this reverse transmission may or may not be the same as the forward transmission. Usually they are the same. So for the time being, let me say it's the same channel which is available for transmission back from user 2 towards user 1, and then it's natural that user 1 will have a similar block to this one, which I can call as the receiver block for user number 1, so that user number 1 receives the signal from the channel and makes use of it. So by a pair of transmitter receivers, we can think of establishing this two-way system. Okay. Usually we'll discuss about one such link, usually say the forward link, while implying that a design has to be done also for a reverse link for a practical system. So for our discussion, we will not explicitly talk about this link, but this has to be there. In many cases, the design of this reverse link is identical to the forward link, but it need not be always. Now, coming to this one link design, I can see that there are some signal processing blocks, like here in the transmitter, like here in the receiver. We know that there are some electronic systems. Okay, in between what I have, can I call this as an electronic system? is a question for you to think. Okay, apparently no. Okay, but the point is, if we have to design a transmission scheme or a forward link, one link of a digital communication two-way system, then we cannot leave this channel out of our consideration. So when you talk about a system, we have to talk about each and everything in between two users. Okay, so it is imperative that we have to understand about the purpose, about the design techniques of transmitters. We have to understand the design techniques of the receiver. We also have to understand this intervening medium, which I have labeled here as a channel. Okay. Now, before I end today, let me ask you, in this description of half of the two-way communication system, is it not that we have to deal with signals and we have to come up with designs of various systems? I think that's the question. Okay, and you will agree to this. If so, can we think of labeling what kind of system is this TX in terms of its features? What kind of system, electronic system, is this receiver, and what kind of signals we are expecting at the input and output of these electronic systems? We will come back to this issue subsequently after we have discussed about a few issues of propagation channels. Propagation channel is a part of this channel here. We will talk about this propagation channel and a few other issues in the next class.